Hey everyone, welcome to the LLM class 2025 from Transformers to GPT. This is lecture 3 today, and we'll kind of pick up from where we left off last time. We spoke about how a two-layer perceptron can learn XOR. We'll actually work out the details today and see why that is the case. So your intuition gets solidified on how these networks behave. Yeah. Some of this might be familiar for you, and some of this might be new. Whichever it is, wherever you are, you can just rehash the concepts and go a little bit deeper. We'll go through activation functions, the different kinds. We'll go through a TensorFlow demo. Back in the days when LLM was not so popular, we used to work with TensorFlow, PyTorch. Even today, I mean, people do work with TensorFlow, PyTorch, but and it used to be like a bread and butter. You have to go through it. Um, I mean, these days, yeah, we do have LLMs come in, but it's not like LLM does everything, and LLM does have issues. So there are certain applications where just like pure deep learning models work really well for production. So, so we'll go through a TensorFlow demo, and hopefully we'll get to this phase where we look into training and backpropagation, right? So also called backprop. And then overfitting and hyperparameters is very important, and other deep learning architectures. So, these things are really fundamentals. Like if we don't have a good understanding of this later on, when you have to, even though it's an LLM class, if you, it's not like in the industry, everything is an LLM. You'll have to work with PyTorch, you'll have to work with other models. And if you have no understanding there, then it would be a serious gap. And also be a gap for, hiring. If you want to get hired into a role, or if you were already in a role but you want to switch to a machine learning role, if you don't have these fundamentals, then it's good luck. So we'll go through it, and all of this, it's like, every year as LLMs improve, we have to reassess where we stand with some of these fundamentals. But so far all these fundamentals are very important, and even if you sporadically look into overfitting or backpropagation or activation functions, it's still important to know that. Yeah. Okay. Before we go into today's lecture, some housekeeping items, right? So officers and reviewers are shared on the web page. Um, so let me just. So this is the web page for the course, and this link should be available. If not, you can copy this link. I think we sent it in the initial email. Maybe we can put it in the Discord again. So the new thing is, so lectures, I think, yeah, all the lectures, the pre-lecture slides, including this one, it's available here. Once we annotate, we add it in here, and then the video recording is added here. The video recording is typically added like uh, 24 hours after the lecture. So within 24 hours after the lecture, you'll find it. So um, yeah, you will not live stream any in-person classes like that we do in person. But this one, like this is live stream, but still the video will be available in a day. And then, and in terms of office hours, right? So we have all the teaching staff's office hours listed here. So mine is on Monday, 6 p.m. after class. Rahul or TA's, his office hours on Tuesday. So that's yesterday, 4 to 5 p.m. And Shillong is Thursday, 4 to 5. And then Bingan, who's our grader, his office hours, I think you'll start hearing from him more from this week or next week once the first assignment starts to get graded. Probably next week. So every assignment, I think you'll get the grade. I don't know if Bingan is here, but you'll get it within a week of the assignment is due. So if the assignment is due this Sunday, you'll get your grade on that by the next Sunday, right? And there'll be some grading hours if you have questions on that. And then we have a weekly review session that's hosted by the TAs. So every week will be kind of alternating between the TAs. So this week I think it'll be Rahul. Last week was Shillong. So the timing is the same for the review session. It's 4 to 4:45 on Friday. Yeah, so these are the resources that you guys have access to. Feel free to use the resources, office hours, review sessions. And obviously you also have Discord. So you can also post questions on Discord. Any quick questions, quick suggestions, pointers, even thoughts, or something that you discovered, you share on Discord. Anything more deeper you want to go in discussion, these officers are very good for that. And the difference between the review session and office hour is that review session will have some presentation for like 10, 15 minutes. That's kind of recaps what was shared in the lectures in that week, followed by Q&A. But office hours is like super open. Um, oh, what happened? Did it change? Yeah, okay. Office hours is like open Q&A, right? So that's the kind of the difference. Okay, any questions on this? Right, and then we have, oh, this page is not up. Okay. Um, yeah, I'll update it, but all the assessments, assignments, they're actually assigned on Canvas, so you'll not be able to see it here. But this tab will probably share some information on assessments, but not like any specific assignment. All of that is on Canvas. I think the references will be updated. Uh, Demos, okay. Yeah, this page has to be updated. Okay. All right. So that's about the web page. Okay, so we covered the housekeeping items on the web page. Um, Assignment one is due this weekend. It's a coding assignment, and so it's going to be a lot of hands-on, a lot of setup, working with APIs, working with the web version of ChatGPT, working with even PyTorch. So you'll get exposed to different elements. If it's new to you, and but you've done, if you've been coding in the past, you can catch up with anything. But if you're having difficulty even after the first assignment, then I think you should definitely reach out to me or the TAs and discuss it. But it should be fairly straightforward, if you're familiar with some of the machine learning coding that you might have done in the past. So that's assignment one. And then assignment two will be assigned this Friday. Again, a coding assignment. I think I also mentioned on the Discord that we'll be having a conceptual assignment. I think we'll get that ready as soon as we can. But that kind of helps you clarify concepts and stuff. So we'll have that.
Professor Mohan.
Yeah.
Yeah, I joined so I started up on the homework and I'm a little rusty, but I took some of the ML classes last year. Um, I was able to get the loss chart and I was working on the confusion matrix, but I was getting a little bit stuck. And I was asking Raul for some help, but yeah, just hoping to see like is there like a framework for getting assistance to just like getting a little bit of assistance with that. Uh yeah, I'm just a little bit rusty on some of that and there wasn't
Yeah.
like a whole lot of
Yeah. I
yeah,
think I think the office hours and the review session should hopefully cover those.
cool.
Um, I think I think Rahul is officers this week. Sorry, the review session this week, and I think the Shillong's officers tomorrow. So I think uh, I think Shillong, if you're here, let's plan to cover some of the confusion matrix. I mean, assignment related concepts and in the review session as well. Okay.
Cool. Yeah, I'll be
Yes,
there. Thank
yes.
you.
Sounds good.
Okay. I see Christopher has a hand up. Yeah.
Yeah, just wondering, are we allowed to use external packages apart from like Torch and NumPy and Matplotlib? Because scikit-learn has a confusion matrix built in, and if not, you could also use Seaborn's heat matrix as a way to get a confusion matrix. Would those be allowed?
Um, I think I'll maybe put it on Discord. The TAs will just review it and get back to you.
All right, thank you.
Okay. Yeah, I think Yanis has his hand up.
Yeah, I wanted to know if the review session will be recorded for those who can attend them.
Yeah, that's a good call out. I think let's do that. So this week it's Rahul, right? I think, yeah. let's do that. So if the TAs are here, let's record the review sessions, and then we can share a link to the presentation portion, maybe the first 15 minutes or 20 minutes on the web page. Yeah, that's a good call out.
Yep.
Yeah,
Sure, we can do that.
sounds good. Okay, anything else? I think get some housekeeping. I'm gonna pause. Okay, so yeah, I think we shared about deep learning reference. I think this is really good. I would say this reference is pretty big, and since we are only covering deep learning as like a background and like fundamentals, you can refer to it as needed. It's not like the main text that you need to go through for this class, but it's just a helpful reference for any of the deep learning concepts we cover in this lecture and next lecture. After that, we'll move on to other topics, right? On the way to transformers and GPT. So, okay. So recap from last time. So we'll do a short recap in every lecture. I think we covered perceptron last time. We covered logistic regression. We'll cover ordinand functions. So we'll just do a quick recap on that. So perceptron is like one of the first like version of neural networks that could discriminate between for classification specifically between positive and negative classes. So it could do binary classification. And perceptron basically looks like this. So you have like three elements, right? So one is the weights. So the weights are important for a single perceptron. So this is a single perceptron. Or you can also say, yeah, single perceptron. I think it's equivalent of a single neuron. Like, okay, obviously artificial, right? So the single perceptron, it consists of one, the weights, two, the summation, and three, the, I guess you can say activation / transformation. I mean, I won't say a transformation because everything's a transformation. So let's not use this word. It kind of overloads it. Okay. Okay, so so 1, 2, and 3, the weights, the summation, and the activation together, right? So together, you take this block. You say, okay, this is my block of the perceptron, and the inputs come in, x1 through xd, and then the output comes out, right? And then after the activation, it's like 0 or 1, right? So these are the inputs. This is the output. And yeah, so let's see. Yeah, so this activation here, yeah, this G here refers to the activation function. So the summation gives you a score. So this is a score. So you just multiply the inputs with the weights, sum it up, add the intercept, and that gives you the score, right? And then the activation applied on the score gives you something that's 0 or 1. In this case, it's a strict 0 or 1 versus soft 0 or 1. It's strict because you have a step function. So anything that's negative is 0. Anything that's positive is 1, right? So perceptron has like a step function, and for that reason, you get a strict 0 or 1. But typically, if you look at neural networks, do you get like very clear zeros or ones? No, right? You get a probability. So how do you get to probability if it's strict 0 and 1 here? By changing the activation function. So when you use a sigmoid instead of like a step function, you get a probability. And the probability is always between 0 and 1, right? So we spoke about, yeah. So perceptron to logistic function is to change the step function. to a sigmoid. So just keep everything else the same, but just change the step function to sigmoid as an activation, and then that becomes like a very simple one neuron and one neuron network, and that's basically the logistic regression. And the sigmoid activation is a function where it's given by g of x is 1 or 1 to the e to the negative x. And in this case, you would change x, sorry, x is, yeah, it's just a function. X is not the input, but you would replace x with a score. So this would be the score. And we know score is W transpose X, right? So sum of the weights multiplied by the, I should actually not use X. It's confusing. Okay, let's use Z. So in this case, Z is equal to W transpose X. And then you apply that and you get a, now you get a probability, right? So now it's going to be a probability distribution. And the probability is between 0 and 1, 0 and 1, okay? In this case, it's a sigmoid. So, I mean, this probability is not the sigmoid function. This function is not the sigmoid function. It's just like saying that across a bunch of inputs, you get a probability across between 0 and 1, right? That's what it means. The sigmoid itself looks like this. So, and because it goes from anything from negative infinity, it goes to positive infinity, okay? And I think this is, at 0, it's 0.5. At plus infinity, it's 1. And at negative infinity, it's 0, okay? So essentially, your score can be anything between negative infinity and infinity. The sigmoid will compress it to be something between 0 and 1, right? And if the score was 0, then the sigmoid gives you 0.5. If the score was infinity, you get 1. So obviously, you don't have to wait for an infinite score. Even if a score is high enough, you see it flattens out. So you'll likely get something like 0.95 for even a score of like 5 or 10. So you don't have to go to infinity, but that's just a function. Okay. So perceptron to logistic regression happens by changing the step function to sigmoid. And we looked at applications of logistic regression, right? We said, where can logistic regression apply? And we said it can apply to, like, as an example, it can apply to learn an OR function or an AND function. And we said, but it may not be able to learn an XOR function. So that's what we said. And we also looked at some logistic regression fundamentals. Logistic regression is a linear model, and it's linear because there's a linear separator. So this is the linear separator. And in this case, it separates, the, class 1 from class 2. So in this case, it's binary class. Okay, so this is, and for a logistic regression, you get a probability. So, like we said, if you use a step function in perceptron, you get 0 or 1, hard 0, 1. But with logistic regression, you get a probability. And the probability is by converting the score into, so you convert the score into a probability using sigmoid, right? Okay, so that is logistic regression, and it minimizes the cross entropy loss. We don't have to go into details on this, but we would probably do that in a machine learning class. So essentially, the prediction from logistic regression is this, right? So you apply sigmoid. What is this? This is sigmoid on W hat transpose X, I. So W hat is the weights that you learn in logistic regression, and Xi is the ith data point. And so the prediction for the ith data point is the Y hat I. Was there any question or? Okay. Okay, so let's talk about, so we spoke about OR and AND. That's an easy example, and there's many other examples for logistic regression, right? What are some other examples where logistic regression can be used, like real life examples? You would have probably seen this in some other classes, or you've probably How many of us have used logistic regression in some capacity in a project or in a?
I think we did spam email detection. I think we used logistic regression.
Yeah, spam email detection. That's right. So is this spam or not? That's the very simple example of logistic regression. Obviously, in the industry, logistic regression would not work as great for spam detection, but it is definitely an application for spam detection, right? I think the earliest motivation was, is this a cat image or a dog image, or, in computer vision, and then spam, not spam, also in computer science, spam email, not spam. Um, I mean, it works if you have good features, but if there's a lot of nonlinearity and a lot of context, then it'll start to not work as well. But that's a real world example of logistic regression, a spam detection, differentiating classes of images, um, and many more, right? Um, Even anomaly detection, you can detect. I mean, it's the same line of spam detection. Is this an anomaly or not? And you can do many things. So, so we said logistic regression is great. It can help with learning simple functions like spam detections in a simple way, or and functions. But we said if you want to learn XOR, this is one of the first function that becomes highly nonlinear. One of the most simplest functions that's kind of very heavily nonlinear, right? So if you have 0, 1, 0, 1, this is x1, this is x2, then you have a 1 for, let's see, yeah. So you have a 1 if it's 0, and 1 if it's 0 if it's 0, 0, it's 1 here and 0 here. So there is no, let's use it this way, 0, 0. So there is no line that kind of we spoke about last time. There's no line that separates it, that all the ones are on one side and all the zeros are on one side. Like you can try putting all kinds of lines, and you'll always find that there'll be a 1 and a 0 on the other side, right? The ones will all not always come together. The only way is if you kind of did this. Okay, this is ones. Everything outside this squiggly line is a 0. Everything inside is 1. So this is the only way, some kind of a way that you can separate out. But this is highly nonlinear. But this is linear, right? Linear, linear, linear. So XOR is one of the simplest examples, to motivate deep learning, where linear separable functions don't work, and so logistic regression won't work, right? Um, and let's actually work out. So in this lecture, right, we'll be a little bit more hands-on. Going forward, we'll assume you know these things, so we'll work on other things, not at this level of detail. But in this lecture, we'll go into a little bit of detail so that you can actually understand some of the fundamentals and you can work through it, right? So XOR can be learned through a two-layer perceptron. So two layers um, is like you have one layer here and then the other layers here, right? So basically this is one set of weights and the second set of weights. So two layers perceptron. And you can basically say if you have these kind of weights here, then if you had different inputs, 1, 0, 0, 1, 1, 1, 0, 0, for all these inputs, you'll get the right right label. So let's look at that. And actually, let's look at the case where you do the two layer, but you don't have the right activation function. You have a linear activation function. So the fun fact is that if you have a multi-layer neural network and all the activations are linear, it is not a non-linear neural network because everything is linear, right? So you might as well just use one layer. The power of a neural network is because the activation functions are nonlinear, right? So I mean, even though we know that, we'll still work through this example and you'll see why the math fails when you look at linear activation functions in identifying XOR, right? So I'm going to just duplicate this. Actually, let me make a table. I think that'd be probably better. So let's create a table. So the x1, x2. So this is x1. Then we have x2. And then we have, oh, you should also identify v1, v2. So then we have, let me use a different color. So then we have V1, V2, and then we have Y. Okay. So this is the setup. Let's also draw this graph again so that, let me see if I can. Can you guys see the graph above? Yeah. So we'll use that graph as reference to compute y given x1 and x2 and assume that the activation function is linear. So activation functions could be, it could be step function. It could be linear. And there's also one more, which we'll cover in a bit, which is ReLU. I mean, there could be a little bit more. And also, we also looked at one more, right? So we looked at sigmoid. Okay. So here we're looking at linear. Okay. And he's saying if I use a linear activation function, which is here, probably not here. We'll use a sigmoid here. Usually at the very end, we use a sigmoid. Let's see. I think let's to simplify, let's use a step function here. Let's use a step function, and then these are linear. Okay. So hopefully the setup is clear. We are looking at what happens for different x1, x2, right? So what are the different inputs that we can have? We can have 0, 0. We can have 1, 0. We can have 0, 1, and 1, 1, right? So let's look at 0 and 0. So what is V1 if x1 is 0 and x2 is 0? So first you have to sum it up. So it's minus 0.5. So let's look at this. X1 is 0, x2 is 0. So then we have to sum it up. So you get negative 0.5 plus 1 times 0 plus negative 1 times 0, right? So you have to multiply the weights here with the values. So you get negative 0.5. And now we have a linear function. So linear function just passes it through just like that. It's not going to truncate a negative. It's just going to pass it like that. So you get V1 is actually negative 0.5. What about V2? V2 is also the same because these are zeros. So you multiply, you get 0, and then you add, you get negative 0.5 here, right? Negative 0.5 times 1. So V2 is also negative 0.5. And then what is Y? So it turns out V1 is negative 0.5, V2 is negative 0.5. So this is a computation for V1. So like Y equals a negative 0.5 plus V1 plus V2. So what is V1, V2? It's negative 0.5, negative 0.5. So what is Y? It's negative 1.5. Again, we have to clarify what is Y. Y is actually passing it through a step function. So Y is actually step function applied to this number. So it's step function of negative 1.5. What is that? What happens when you apply a step function to a negative number?
It's 0.
Zero.
It's 0 because anything on negative infinity on the negative side is 0. Anything on the positive side is 1. So does that make sense? Why is 0? Okay. Now let's look at x1 equals 1 and x2 equals 0. x1 equals 1, x2 equals, so this is, we have to look at V1, right? So x1 equals 1, x2 equals 0. What is V1?
0.5.
0.5. And then what is V2?
1.5.
It's negative 1.5, right? Because if you look at V2, this is negative 1 multiplied by 1, and then negative 0.5 here. Here, sorry, this one.
Okay,
So we'll
okay.
look at
Again, welcome. My name is. If a security operator or a system operator were to look at an.
Hey, that's Professor Pravendran.
Okay. Stony is with the professor. Okay. All right. So V2 is negative 1.5. Yeah, that makes sense. Okay, let's put that down. So this is 0.5, negative 1.5. And what is y in this case? Y is the step function applied to negative 0.5 plus 0.5 minus 1.5, which is so this is negative 1.5 again, right? So step function applied on negative 1.5 is 0. Makes sense. And if you did the same as 0 and 1, what do you get? You get something here, but very likely 0. If you do it here, you get 0. So essentially, regardless of whether it is 1, 0 or 0, 1, maybe this is, I have to check if 1, 1 is, if one of these, I'm very sure this would be 0, but 1, 1, I think you just have to check. But, you know, this is clearly, you're not able to discriminate. This is not XOR, right? Because 0, 0 should be 0, 1, 0 should be 1, right? And so using a linear function doesn't work. Okay, so now let's switch to a step function as an activation. So we use step function as an activation at the very end. What if we use it here as well? Right, we use linear function in V1 and V2. What if we used a step function there? Let's actually look at that. So this is y with a linear function. This is, oh, the V1s and V2s would change. Yeah, but that's okay. We can figure it out. So I want to do it here because the graph is here. I don't want to restart another. Let's say this is y with step functions. Okay. So now, if v1 is negative 0.5 and a step function is applied, what happens to it? You get a 0, right? The same here. So this would be 0. This would again become 0. V2 is negative 1.5, passes through a step function. So right here, V2 is negative 1.5 if you had a linear function, but if you had a step function, it becomes 0. So now you have 0.5. So this is 0. V1 is 0.5. V2 is 0. And so you get 1 plus negative 0.5 plus 0, which is 0.5, right? So you get a y that is 0.5. What is step function applied on 0.5?
1.
That's 1. Okay. Okay, so now we got the right answer. So you got a 1 for a 1, 0, and you got a 0, 0, you got a 0 for 0, 0. And if you try it again for this, you'll get 1 here and 0 here. So just the fact that we changed the linear activation to a step function, we could get the right response with a 2-layer neural network. So we just showed that a step function based, of course, step function is not practical. We don't use it in practice, but we'll have a way to replace a step function with something that's still nonlinear, but something that's more practical. And the reason step function is not practical is because it's not differentiable. Okay, there's a sharp, point of non-differentiability at this 0. And so it's not used in, if you look into PyTorch, you look into TensorFlow, you look into any LLM model, you'll not have any step functions there, but you'll probably have other substitutes for it like ReLU or tanh or other activation functions, right? Okay, so using just linear activation, it's useless. You can have as many layers as you want, it would not work. It's because you're having a linear activation function. But using a step function with just 2 layers, we could learn the XOR function. Yeah, does it make sense? So these two, I would say, we didn't do it, but you can do it as an exercise to see that you're actually getting the right answer. Okay, so just to recap, so one 2-layer perceptron, let's say 2-layer neural network with linear activations on hidden layers fails, right? So why hidden layer? Because this is the hidden layer, right? This is the hidden layer here. Why is it hidden? Because it's sandwiched between the inputs and outputs. So it's a hidden layer. And this is one layer. You could have many layers that are hidden, right? So like if I'm a consumer of a neural network, I only give it an input and I get an output. I don't see the in-between layers and what the outputs are. So that's why it's hidden. So if we have linear activation in the hidden layers, we just saw that it fails, right? On the other hand, a two-layer neural network with step function as activation on hidden layer succeeds. Fails for XOR, right? Okay. So the power of neural networks, the reason it's starting to work is because of the nonlinearity. And even though it's a simple function like step function, or we'll also see something like a ReLU function, right? This is ReLU, this is step. When you put together multiple layers with similar structure, it was said that deep learning can learn pretty much anything. It can learn to approximate any function. The power of neural networks in deep learning came because you could stack these layers one after the other, and you could have these nonlinear activations that could then learn a very complex function. So essentially, a very complex function can be, if you had enough layers and if you had enough data, that's another thing. It's not just enough layers, enough data and enough layers, you could pretty much learn anything. And we'll see a demo today that kind of illustrates that. Okay, so just as a quick recap, just take a couple of minutes to look on this question, and you can put in the chat what your answer is. You can just take a minute and just see what's coming up for you. Yeah, so decision trees can definitely learn an XOR function, right? And logistic regression, we already covered, would fail to learn an XOR. And SVMs, if you have a nonlinear kernel, maybe, but you don't hear about SVMs anymore. It's kind of a thing of the past. Like there used to be a time when the SVMs were very popular, and then deep learning happened, and then deep learning was very popular. Now it's like even deep learning is something people are like, oh yeah, I used to use it before. Now it's LLMs, but deep learning is still kind of the building blocks, right? It's a foundation. So yeah, definitely decision trees can learn an XOR function. Okay, so so a little bit of like if you look at the math behind the two-layer neural network, if you had one hidden layer, what you would do is you would first get the outputs on this layer, which is the activation function applied to each of these, and then you get something here, and that something is represented by this equation because it's the score coming out of the inputs here and the weights applied on that. And you do the same for each of these neurons. So you have 3 neurons. So each neuron, so here k equals 3 in this graph. So you have 3 neurons, each neuron gets its own score, and then you apply an activation function on it. And then the output is, again, you compute the outputs by, I think, so this is showing multiple outputs, but anyway, if you had a single output, then you basically get a score out of the 3 neurons here and apply the activation function, right? So just a little bit about the math behind the neural networks. And maybe we'll get to see a little bit of the math in the conceptual assignment too. Because otherwise you would just be working with libraries in Python or PyTorch, and then you would not actually go into the math. But this is probably helpful in that perspective. Okay, let's look at activation functions. So we said step function is definitely something that works, but it's not differentiable, right? At 0. And people found that sigmoid is great. Sigmoid is a nonlinear activation function. It's differentiable, but it's not. It's useful only in the output neurons. It's not so useful when you put the sigmoid in the intermediate or the hidden layers, because the gradients kind of saturate, activation saturates. So there is a kind of an issue with this sigmoid, and so it's usually used in the output layer, and it's called softmax when you do that. So you get a soft assignment or a probability coming out of. So definitely useful for the output layer. But the popular choice for intermediate layers has been a ReLU, or rectified linear unit. It's basically the function is basically the max of 0 and x. So anything that's negative, you set it to 0. Anything that's positive, instead of setting to 1, you just set it to itself. So unlike step function, it looks like this. So this is step function, but it looks like this. And then obviously the ReLU will keep going up like that. So whatever the x is, if it's positive, you just get that. The only issue with ReLU is that during training and, especially during training, the neurons can die because you just encounter a negative score, and then the negative score gets set to 0. And if it's 0, it stays 0. So there is some issue with if you have an input that generates negative scores and then things die off, then there could be an issue. There could be an issues in training, right? So it still works great. I mean, it's ReLU is amazing, but to just improve it, they've come up with leaky ReLUs and noisy ReLUs, right? So leaky ReLUs look like this. So you instead of setting it to 0 if it's negative, you allow for a small value if it's negative, right? And the value is proportional to the input. So, but that's, you would have like 0.01 or something very small as the coefficient here. And so you would assign a small non-negative, small value for the activation, even if it's negative. But you're not set it to 0. So that's leaky ReLU. So leaky ReLU could be like an improvement. And these are things that you don't get to see until you open a PyTorch module, and then you actually start investigating what's inside, what are the activations actually being used, and what's actually working. But if you did that, you'll be able to see that people are made these choices and it works really well. Okay. Let's see. Okay, I would love for you guys to actually work this out. We didn't look at ReLU, right? So if we can make a table, we'll go to a breakout now. You can take like 10 minutes and definitely get some pen and paper, because this will be one of the breakouts where we actually get to work on these numbers. It's good if you can build a table just like what we did. So you have x1, x2, v1, v2, and y. And assume that at the very end, you have a step function here. Yeah, step function. Okay. So you have step function here, and here you have a ReLU function. Okay. So if you had a ReLU function intermediate in the hidden layers, and you have a step function at the very end, for 0 and 1, 1, 0, 0, 0, 1, 1, what would be the values of y? And actually, let's say this is the y before you apply the step function, and then there is a. So what you want to know is, before you apply the step function, you get a y, right? So for what weights would you get a value of y that's greater than 0.7 for these two? And then, so you want this to be greater than 0.7 here, and you want this to be less than negative 0.7 here. Okay, so for what values of these would you get this? Okay. And then clearly, I mean, I'm very sure that this will be right. So this will be 1, 0, 1, 1, 0. So there's no issue here, but the reason to do this is because you're more confident. If the value is exactly 0.5 and then you kind of convert it to a 1, that's not so confident. So I want the weights, if we want to see if you can position the weights in a way that you can actually get a good confidence rather than it just being on the borderline, right? So yeah. So is the question clear? Yes. So my suggestion is, like, the PDF is available on the web page. So if you need to reference this graph, you'll find it there. So just construct this table and compute and, maybe tinker with these weights. You'll have to just tinker with, the hint is to maybe change these two and then compute V1, V2 so that your Ys are well positioned. And also definitely your step function should be in this, you should get an output that looks like this. Okay. And we're using ReLU functions here. So let's, I'll put you guys into a breakout and, just get a pen and paper and you have 10 minutes, just work through it. And hopefully you're able to share some weights that you found were conducive to get a good confidence on why for the ReLU function. Okay, recording. So let's talk about overfitting. Overfitting is less of an issue these days, but it's still there. We say LLMs, for example, they've trained on the web, they've gone through all kinds of data, and they've seen enough data. Maybe they don't overfit, but they still behave based on the data that they have seen. Even if they have seen like, 50 million books equivalent of data, they could still be biased by what the LLM has seen. So if there is insensitivity in the response, it could be coming from the sources that it's referencing. And so that's a different level of overfitting. It's not traditional overfitting, but it's like more complex, and that's where responsible AI comes into play. But in traditional AI models that are not LLM based, overfitting is even more of an issue than LLMs, for example. And so let's just quickly recap the concept of overfitting. So I'll kind of draw three boxes here. So one is, let's look at underfitting. Okay. And then we have the right fit. Oh, shoot. Right fit. And we have overfitting. Okay. Let's look at two sections. One is regression. The other is, say, classification. So these are two classic problems, right? So let's look at some data. So let's say the data was something like regression, right? So let's say you have data that looks like this. Let me think about this. Yeah. So let's say this was height, and then this is weight. And let's say there was this point, a couple of points here as well. Okay. So this is like a typical, as your height is increasing, your weight is typically increasing, but you can't just say exactly for this height, this will be the weight. There'll be always ups and downs, right? So this is a graph that looks like that. And so maybe, it's not linear. I'm just making a guess here, but let's say a right fit would look something almost linear, but it's a little bit of a thing here. And it kind of ignores these outliers. These are outliers here, right? Because yeah, so that's a right fit. And now let's look at overfitting, right? So overfitting would do the same thing, except, you have these points. And then you have these outliers. Overfitting would say, oh, I think, the graph looks like this. Yeah. So if you use the overfitting based model, you'd say that for a particular height like this, you will see really low weight. Does that make sense? No, right? But overfitting is trying to overfit to the data that it's actually getting to see. And it's actually looking at outliers too. So obviously you can say I'll screen for outliers, and you'll still have overfitting if you specialize to the data that you're training on, right? On the other hand, underfitting looks like same data. Underfitting would say something like, you know what, just take the average. Okay. So everyone is 140 pounds. That's it. I'm done. Regardless of your height, I think the average weight is 140 pounds. That's it. Give me a weight 140 pounds. That's it. I'm not going to do better than that. So that is an extreme example of underfitting. Is I really don't care. I'm just going to give you one number, or I'm just going to be a very simple model. I'm not going to look into any nuances. The right fit is the one that's somewhere in between overfitting and underfitting, right? So we want to have the right fit. And this has been a problem a lot for even deep learning models because of the number of parameters they have. But as long as you have enough data, and in two specific applications like natural language and images, you can get away with lots of data, especially language, right? In NLP, you can generate a lot of data, and you can mine the web, and you have so much data that you typically don't overfit in the traditional sense. So you can, and that's how you're having like, millions and millions of parameters in deep learning models, because you have hundreds of millions of data points to take care of those millions of parameters, so that even with a couple of passes over the data, you can still avoid overfitting issues as much as traditional AI models. But the problem is that, another way to look at overfitting is like when overfitting happens, right? When number of data points is less than number of parameters. This is like it's like a thumb rule. If you look at this crazy squiggly up and down function, it must have a lot of parameters to describe all the movement, even in this two-dimensional space, right? On the other hand, if you look at this one, this is a right fit because probably the number of data points is greater than number of parameters. Yeah. And so you have kind of a right fit. And in this case, underfitting is just like, I'm not using the data, or my model actually is very, very, actually you'd say something, number of data points is much, much, much bigger than number of parameters. So I have lots of data and I'm not really using the power of data. That's underfitting. Not using the power of data is underfitting. Using the power of data is right fit. And extreme usage of the training data and overfitting to it is overfitting. Yeah. So you're trying to force fit a very complex model onto limited data, that's overfitting. So we typically want to be in the right fit zone. And the same would hold for classification. So, you would overfit because of some outliers and so on. So you can do the same thing. I'll just probably demonstrate overfitting for classification, and then we can go to the next topic. Okay, we have time. All right. Yeah, we have time. I just want to do probably a demo and then we can finish. So overfitting in classification would look something like this, right? So let's say you have X's that are one class. And then you have Y's that are other class. So overfitting would kind of really try to go through, like follow the contour, and you might get something like this, right? This might be the overfitting classifier, whereas the right fit would probably just say, hey, these things, they're kind of like outliers, so don't worry about them. So your right fit might look something like that. Okay. Does it make sense? So worrying a lot about every single data point in your training data leads to overfitting. Assuming that your test data and validation data, which is something you may not see, might have a little bit might have a little bit different patterns, and allowing for that is going towards the right fit, right? So overfitting has been more of a traditional AI issue, but it's still useful to know in today's context. Okay, so I think I'll finish with a TensorFlow playground demo. I think this is a very useful one. We'll not be really looking at overfitting, but we'll be looking at underfitting issues in this and getting the right fit. Okay, so let's look at the demo. Okay, So we'll just go through a TensorFlow playground demo. And this is very instructive to understand how the concepts of overfitting, underfitting, especially I think underfitting and right fit comes into play here. So we're looking at a neural network with different number of layers, different activation functions. We looked at activation functions here. And then there's also regularization. We'll probably not get to it. And let's look at classification. We looked at regression in the lecture, but we also looked at classification. So we'll focus on classification. And let's actually look at this example. So this is a data set, right? So if you can see the yellow points and the blue points, and any line in between that's linearly separable will do the job. So we're just looking at a linearly separable use case. So do we need hidden layers here for this one, for this example?
No.
No. Based on what we saw, a logistic regression could very well do the job. So let's reduce the hidden layers to 0. So you have 0 hidden layers. And it just takes a linear combination of the weights, and then it applies a sigmoid. So here the activation, I believe, is only for the hidden layers, so we don't have to worry about it. But I think a sigmoid gets applied. And let's do a training. So now the training is done by executing this. And let's look at, there you go. So the training is done. I can stop it. 580 epochs. So it's gone through the data set so many number of times, many times. This too many, way too many. Let's stop there. We usually don't go beyond a few epochs. So the training loss and test loss is 0. So loss being 0 is perfect, but you typically don't see it as, in practice. But this is a really small data set, and it's two-dimensional in nature, and it's a perfect separation. So you can expect, in this case, the training loss and test loss can be 0. So and you see this white line here, that's the line that's the weight vector. So the weight vector is in 2 dimensions, and it's pointing this way. So what is the weight vector? It's actually pointing this way. So it might be something like 1, 1. That's the weight vector. So W1 is 1 and W2 is 1. That's how I see it here. So that's the weight vector that got learned through a logistic regression, so no hidden layers for this data set. So that's great. Is this an example of overfitting, underfitting, or right fit?
Right fit.
This is a right fit. Okay, great. Let's go to another example. So this is, one circle of data points within the other, right? Two concentric circles. I mean, yeah, not exactly a circle, but you have, you have like kind of 2 rings, let's say. And let's do the same thing. And you see, yeah. So what's happening here? Is it underfitting, overfitting, or exact fit?
Underfitting.
Underfitting, like it's not able to separate out, it's trying its best, but it's not able to separate out the white from the, yeah. So that's not working. And let's try it adding some hidden layers. Let's try with 1 hidden layer. Maybe we use a ReLU activation, like we discussed ReLU. Okay, ReLU likes to, it's kind of sharp lines. So you can see it's trying to get there. It's doing better than like just logistic regression, but you can see these yellow points are not able to be covered, right? So let's increase the number of neurons. Maybe we can make it 4 neurons. Okay, so ReLU activation with 1 hidden layer. So that's 2 layers in total, and 4 neurons instead of 2 could get us to separate 2 concentric circles, right? When a logistic regression could not do. So this is you can see the train loss and test loss are close to 0. This is an example of a right fit. Of course, training loss and test loss don't have to be close to 0, but the lower the test losses and the lower the training losses, then you're doing a good job. So this is good. Now let's look at this. What is this function? This might remind you of something.
Is this the XOR?
This is like the XOR. It's not exactly the XOR, but it's a XOR-based data distribution, right? Because the yellows are in the 1, 0, 0, 1, and then the other ones 0, 0, 1, 1. It's kind of like that. But it's not the XOR function. It's just like it looks like that data distribution. So let's try with. Okay, so this is clearly bad. We'll stop. Let's add one hidden layer, 2 neurons. Trying its best, but you can see the whole of orange is in the blue segment. Okay, it doesn't work. Let's make it 4, just like we did with the previous one. It's kind of doing a better job, but still having issues with some of the blues in here. Okay, let's add one more layer. Okay, how about this one? Is this a right fit? Yeah. And what would you say this is? Oh, this is also good. Let's think 2 layers did the trick. Is this underfitting, overfitting, or the right fit?
It's right fit.
Looks like the right fit. Yeah. So this is even better fit than the one before, right? It's really captured the.
Yeah.
So with 2 hidden layers that happen, and then enough number of neurons. You have to have enough neurons. If I made it 2 neurons here, you don't get the same. Yeah. Okay. So that's one, and then we have the spiral. So clearly no hidden layers will not work. So let's try this one. It's failing. Yeah. So this is also underfitting, right? Let's add one more layer. Okay, look at that. So if you look at this graph, right, this is very instructive. As the epochs were going, you can see there's a test loss and training loss. So typically this region is overfitting region because the test loss seems to be diverging from the training loss. But at some point, both the training loss and test loss start to go down, and then it's still oscillating a lot. It's like there's kind of uncertainty and it's not able to converge. It's kind of doing better, but there's definitely points that it got wrong. Let's add one more. Let's see what happens. Okay. So you see the train loss and test loss are hovering around 0.0 something. Seems to have done a better job, but it's really, I mean, if this is the real data, then that's great. It's probably a good fit, but it could also lead to overfitting if this is not the real data. So, but you can see that with this function with concentric, with a spiral, right? Like I think we had this spiral within a spiral, or what do you call this? Concentric spirals. We needed enough hidden layers to, get to the right fit. But nothing to say that this may not lead to overfitting in a different data set if you use the same kind of function, because the more complicated these nonlinear functions are, the more they can be prone to overfitting. So it looks like a good fit on this data, but we never know. Okay, so anything else here? Yeah, learning rate also matters. If you change the learning rate, things change. Let's try a more aggressive learning rate. Let's see what happens. Let's restart. Oh, look at that. Look at that. See, look at why is this saying 0.473 and 0.427? But interesting. Okay, this is way too many epochs. Anyway, let's add some regularization. I think this is something we haven't covered yet, but it can be helpful to take care of overfitting. Let's look at, oh, we have no regularization rate. So let's make it something. Restart. Okay, look at that. There is less of an oscillation and a gap between the test and the train, right? That's because of the use of regularization. Regularization makes sure you're not prone to overfit as much. So it's looking a little bit more cleaner as a function than what we saw earlier. Although it is still clunky, it's looking a little bit more cleaner. So that's how regularization can help with overfitting issues. Okay, yeah, is anything else you want to talk about here? Yeah, and if you change the activation, oh, let's do this. Let's make the activation function sigmoid. We said sigmoid is not good for in hidden layers, right? In theory. So let's see if that's true in practice. So let's pick XOR. Does anyone remember how many layers work for XOR? 2? 2 hidden
Yeah,
layers?
2 layers.
2 layers work, right? And we had 4 neurons. Let's try that. Oh no, what happened? So sigmoid isn't working as well. I think, again, we said this like training issues if you use sigmoid as hidden layer activation function, right? And we see that happening. It's kind of flattened out at the training loss of 0.78 and test loss of 0.526. But I keep everything else the same. I change it to ReLU and look at that. So just the choice of activation function makes a big difference in getting a deep learning model to work. So we saw that example here. And linear, obviously, linear would be really bad anyway. So we said, we looked at mathematically why linear activation doesn't work for XOR. And now you see through this playground as well that that's the case. And we also still saw why ReLU is much better than sigmoid for training. Okay, any other questions or thoughts on this before we close? There's a few other nuances here, like, these things, these are nonlinear features. So if you include certain things that are nonlinear, even a logistic regression will work. So let's look at an example. So let's look at XOR. X1, X2 is a nonlinear feature, right? X1, X2 is 1. Let's see. I mean, this is not exactly XOR, but if you look at the points in the orange, right? The product of X1, X2 is negative. Is that right? If you look at the points in blue, the product of X1, X2 is positive. Is that right? Yeah. You look at any of the boxes, you'll find that pattern to be true. So if I use X1, X2 as a feature, and if it's positive or negative, I instantly know, okay, just focus on that feature. If it's positive, X1, X2, then you're good. If it's negative, then it's orange, right? So even with 0 hidden layers, and then if I use this as a feature, look at that. You get a perfect classifier. So this is with logistic regression. It's not that logistic regression, is a bad model, but if you have the right feature, if you do the right feature engineering, you will be able to do perfect classification. But how do you do right feature engineering? This was a big issue in the earlier days. And that's where deep learning came in and said, don't worry about it. We'll take care of it. The earlier layers of a deep learning model do the feature engineering for you. The later layers do the actual classification and the actual task. So we'll look into more of this in the next lecture. Yeah. So I think we'll stop here.